Hi everyone, and welcome to this discussion of systems of nonlinear equations. So we're going to talk about three different methods that I like to use to solve systems of equations that are not linear. These methods are going to be very familiar, hopefully, if you've ever learned how to solve systems of linear equations. The three methods we tend to use are substitution, elimination, and graphing. The first one, substitution, we use this when one equation can be solved for a variable, or you can solve for an expression that shows up in the other equations. For example, if both equations have an x squared, you'll get the x squared alone in one equation and then substitute into the other. Now, elimination, we use this when the equations have the same variables raised to the same power. So maybe you have an x and a y squared in both equations, and those are the only variables that show up in both equations. That's when you can use elimination. And graphing, we want to use this when you can solve for y in both equations. Now, because these are nonlinear equations, just be careful, because when you're getting y alone, if you have to do like a square root, don't forget the plus or minus sign, and you're going to actually have two equations that need to be graphed. So let's take a look at some examples of how to do this. In example 1, it says to use substitution to find all the solutions of the system. Now, notice in our system, this is a linear equation here, bottom one. The top one is not linear. It's actually the equation of a circle, if you recognize that. Now, in this one, they've specifically said substitution, but substitution is a good choice because notice if I add y to this side and subtract 10, I can get y completely alone. Now, another thing you could do is use graphing on this one. We wouldn't want to use elimination because the variables are to different powers. So I'm going to use substitution. I'm going to solve the bottom equation for y to get some expressions that I can substitute into the other equation. So I added y and subtracted 10, so y equals 3x minus 10. And then I took this expression and put it where the y was in the first equation. Now notice in this one, to solve this, all the y's are gone, so I just have to solve for x. And the way we do that is we would square this binomial, combine some like terms, get everything to one side, and find the zeros, because this is a quadratic equation now. So to square the binomial, you would do 3x squared, which is 9x squared. Then you would do 2 times negative 10 times 3x, which is negative 60x. And then you'd square the negative 10. Now, that is a special pattern for a perfect square trinomial. If you don't know that, just use FOIL or distributive property. Just multiply it together, and you will get this expression. Now I need to combine my like terms. X squared plus 9 is 10x squared. I still have the negative 60x. And if I subtract the 100 to this side, which I need to do in order to find the zeros, they will cancel each other out. Now I need to factor by a GCF. So the GCF is 10x, and I'm left with x minus 6. And the zeros, this 0 is 0, because if I put a 0 in for x, this part will be 0. And the 0 here is 6, because if I put 6 minus 6, I will get 0. So my zeros are 0 and 6. Now, the last thing I need to do is take these and put them into an equation, one at a time, and find out what the y would be. And I'm going to use the bottom equation just because it's a little simpler than the top equation. But you could use the top equation and it would still work. So when I put 0 into that equation, I got 0 minus y equals 10. So y is negative 10. And when I put 6 into the bottom equation, I got 18 minus y is 10, and y is 8. So my answers are the points 0, negative 10, and 6, 8. Okay, so let's take a look at another method for solving these systems. In example 2, it says to use elimination to find all the solutions of the system. Notice the system that they gave is this one. See how the x's are both squared, the y's are both to the first power. And those are the only variables I have here. So because these variables appear the same way in both equations, I can use elimination on this. So I think I'm going to eliminate the x squared term because it'll leave a simpler equation to finish off. So let me show you how that's done. Okay, I multiplied the top equation by 5 and the bottom equation by -3. And my goal with doing that was to make sure that I had the same coefficient with different signs here. So now I can add the equations and the x squareds will cancel out. My y's, I'll have 10y minus 21y is -11y. And I'll have 130 minus 9, which is 121. Now that I've added the equations, I just have a one-step equation to solve. I just divide by -11 and find out that y has to be -11. Now to find the x's, I'm going to take this and put it into one of the equations and solve for x. So I took -11 and put it into the first equation for y. So I put it right here and I did 2 times -11 and I got -22. Now to solve, I'll just add 22 to this side. I divided by 3 and I did a square root. Now anytime you do the square root, you need the positive or negative sign there, unless it's an application question where it doesn't make sense to have a negative value. So my x's are +4 and -4. So I have +4 and -11 for one solution, and -4, -11 for the other solution. We have one more method to talk about, and that's graphing. So let's see our last example. In example 3, it says to use graphing to find all of the solutions of the system. They give us this system right here. Now this one's set up nicely for graphing because I can easily get y alone. I would just add y to this side and subtract 2. I'd add y to this side and add 1 to that side. So it's very easy to get y alone. And so that's what I'm going to do. And then I'm going to graph it on my graphing calculator. Okay, so these were the equations that I put in to y1 and y2. And then my graphing calculator showed me this. So I see that it looks like they cross at -1, -1. And at 3, I think that's 7. 1, 2, 3, 4, 5, 6, 7. 3, 7. So what I need to do now is check those points because it appears to cross, but we need to make sure. So all I'm going to do is take the x value, put it into one of the equations, and make sure I get the y value that matched. And then I'll do the same thing for the... Okay, so I have to substitute those points into both equations just to make sure that both equations still remain true. So for the -1, -1 point, I put in to the 2 times x minus y equals -1. And if you calculate this, it is actually equal to -1. And then in the other equation, I did -1 squared minus the y value equals 2. And if you calculate this, it is also true. So the -1 point is a solution. Now we have to check the 3, 7 point. So I did 2 times 3 minus 7 equals -1, and that is true. And then in the other equation, I did 3 squared minus 7 equals 2, and that is true as well. Since all of these are true, both points are the solutions. Now, if you had checked your answer and maybe this equation here did not work, then 3, 7 may not be a solution. Just double check your math to make sure that you did it correctly. If it doesn't work, it's not a solution, and you would only keep the 1 point. Okay? So that's it for solving systems of nonlinear equations. Please let me know if you need help with anything.